Welcome everyone to this mini course on parametric lattice structures using ELISE, together with Solo Lattices, Mocha, and Dendrise plugins. My name is Samuel. I am co-founder at Solo Lattices, and I am the lead technical and software solutions architect for all our work, including Mocha and Dendrise. I studied computer science and have done work in many different areas. Most of my previous work concerning this topic was developing internal tools with Rhino and Grasshopper 3D, back when our company was offering lattice design services. But that's enough about me. Let's talk about the course. The main objective is to familiarize users with the creation of parametric lattice structure workflows in ELISE using Mocha and Dendrise. It's a short course, but very dense, and we will be looking at how to think and talk about lattices, how we can create conformal and cell grid lattices using Mocha, accompanied by Dendrise, and then, towards the end, we will look at some more advanced applications, for example, simulations. Throughout this course, we're going to be using the Mocha and Dendrise plugins, which you should already have installed. You can find these components in the ribbon section of the UI in their respective tabs. So, let's first have an introduction to Mocha. Mocha was made to make lattice generation easy and intuitive, both for designers and engineers. It was born out of the experience we had using Rhino and Grasshopper 3D. We made many lattice projects for many clients, and we know all the pain points and all the difficulties that engineers and designers find in the way. Mocha seeks to ease this integration of lattices into designs that may be new or pre-existing, and wants to allow you to use lattices in new and innovative ways in the ELISE ecosystem. But first, we have to learn how to think and talk about lattices. Most of the time, when we talk about lattices, be it beams, surfaces, triply periodic minimal surfaces, we are referring to a periodic structure, a structure that repeats across space. Therefore, we often think of the unit cell of a lattice, the base unit that repeats across space. Usually, when we design lattices, we are filling a volume, be that volume an explicit region of your design or an implicit region of the design space calculated parametrically or through other methods. In both cases, we often have an inside region, which we can call the infill, and a border region of the lattice, the skin. The way these two regions interact is crucial to create well-designed lattices with the desired mechanical and aesthetic properties. So, Mocha gives you ways to create these lattices through two main classes. Conformal lattices, which you can see on the left, fill any closed volume. The skin of these lattices will automatically conform to the surface of your design space, as you will see later in the demonstration, making it very flexible and easy to use when all you need to do is to fill a volume. Think, for example, of lightweighting. However, these lattices cannot be customized a lot due to inherent limitations in the way they are generated. That's why we have grid lattices. Grid lattices consist on the creation of a grid that can be adapted to multiple reference geometries, such as surfaces, volumes, points, and this can be, again, part of a pre-existing design, or maybe you generated them parametrically. Once you create this grid, you can populate it with pre-made or custom cells of your own design. This type of lattice is very customizable, but it also requires more expertise and experience to use. So Mocha gives you tools to create both types of lattices. You can create volume stochastic lattices or volume filling lattices using regular geometries, and you can also create and modify these cell grids that you can then populate with either pre-designed or custom cells, and you will see more later on in the demonstration. But first, I want to talk about Dendrise, which is an aid to play with this complex geometry. Why? Because lattices, as you might already know, can become extremely complex, especially when you have large design spaces. Therefore, they can be difficult to represent efficiently on a computer and also complicated to operate on. Traditionally, we have two geometrical representations: NURBS, which are very heavy and difficult to render, and they're also notoriously difficult to operate with when they get very complex. Think, for example, of Boolean operations. We also have mesh representations, which are easier to render, but they also do not offer very robust operations. Think of unions, intersections, hollowings. Mesh, especially when it's a complex mesh, they don't often play well. So what's the solution? We need alternative geometrical representations. Right now in the market, there are two main types: voxels, which are used by Dendrise, and implicit fields, which are used by software such as in topology. Dendrise is a voxel engine that is optimized to aid you in the design of complex lattice structures, and it can also be used with other types of geometries. It includes features such as easy Boolean operations, such as union differences, intersections, even offsets. It also has a variety of smoothing algorithms that help you achieve that nice organic look in your geometry. It can convert mesh to volumes. Volume is the native Dendrise voxel representation, and also volume to mesh conversions, obviously. And we have a lot of features upcoming, such as masks and blends. So keep an eye out for that. Together, Mocha and Dendrise form the perfect duo. Using Mocha, you can create your lattice skeletons, which can be curves that will be later turned into beams, or surfaces that will be later turned into a surface lattice, or any type of morphable geometry. And then you use Dendrise to create a volume, a geometry that you can actually manufacture, because you cannot 3D print lines. You need actual beams. With Dendrise, you can create this closed geometry that can then be manufactured using different methods, such as, for example, 3D printing. But that's enough theory. Let's get to the practical.